Hello everyone, welcome to RASAAYANA Institute of Sciences. In this video, we are going to discuss about what is the acidic relation between phenol as well as benzoic acid. So generally we know that phenol as well as benzoic acids are acidic in nature, and what will be their pK values and how one acid is going to be related to other acid, which is the strongest among them, and what is the reason for showing high acidic character and low acidic character. Everything will be discussed in detail. Okay, now see this. Phenol is generally represented like this. So they are also called aromatic alcohols. Already I explained. So after losing proton, there is a formation of a phenoxidine. After losing proton, there is a formation of a phenoxidine. Phenol and phenoxidine. And if I take benzoic acid carries C double bond OH group, and it is attaches to benzene directly. So during this situation, benzoic acid, after losing proton, there is a formation of a benzoate ion. This is called benzoate ion. Benzoate ion, and this is called benzoic acid, and this is called phenoxidine. Phenoxide ion. Now, these two acidity, if I take this as molecule 1 and this as molecule 2, these two acidities depends on these two conjugate bases. So now it is a conjugate base of phenol. It is a conjugate base of benzoic acid. So this phenol acidity, how it is explained by this conjugate ion, and this benzoic acid acidity, how this conjugate base is explained, now we are going to discuss clearly. See, every time remember, acidity depends on, always acidity depends on stability of conjugate base. It is depends on stability of conjugate base. So what is the conjugate base of phenol? Phenol conjugate base is phenoxidine. So now I am writing phenoxidine. This is phenoxidine. Phenoxidine is stabilized by resonance. Now I am going to write one of the resonating structure. It will be resonates and give carbon with negative charge. This is double bond O and this is negative charge. Like that, this negative charge is keep on delocalizing from one place to other place. So it will be migrated like this. This is delocalized anion, and this will be migrated and this will be transferred here. Double bond, and this is anion. So they are the resonating structures of phenol. Okay, this is your molecule 1. Now see, this is resonating structures of benzoic acid, which is responsible to give benzoate ion. In case of benzoate ion, C double bond O minus will come. This C double bond O minus, this negative charge will migrate here and this will be transferred here. Okay. Now you may expect only two resonating structures over here. This is C double bond O and this is O minus. So it may be delocalized right to left, left to right like this. But here see, this O minus delocalizing from oxygen to carbon, and this carbon to here and this carbon to here. So almost all with benzene, three resonating structures are expected. Additionally with O minus. But see, in this case, when benzoic acid after losing proton forms a benzoate ion, this will give only this kind of resonance. Now benzene is not contributing in this one. Okay. So here we are getting more number of resonating structures as compared to benzoate ion. So generally we know that as number of resonating structures increases, stability increases. But here in this only two resonating structures we are getting, but here we are getting more number of resonating structures. So generally phenoxidine is more stable as compared to benzoate ion based on this statement. But actually benzoate ion is more stable as compared to phenoxidine. That is the actual reason. Reason for this stability is equivalent resonating structures. See, this is equivalent resonating structures and this is called non-equivalent resonating structures. What is the meaning of equivalent and non-equivalent? Equivalent resonating structures, nothing but, see, these two are undistinguishable. We can't separate them. Both are almost all same. But in this case, what happens? See, energy difference between these two is very small. Small energy difference is there, which means we can interconvert them very fastly with less energy. Almost all both are same. But in this case, this anion is different as compared to this one. This is different as compared to this as well as this. So there is a high energy gap between one resonating structure to other resonating structure. So generally we can say this is called energy gap between one resonance form to other resonance form. So interconversion is not easy. Much more energy is wasted here itself. So we can say that benzoyetine is more stable as compared to phenoxyetine, because here different resonating structures, but here equivalent resonating structures. Okay. So finally, one conclusion: if you compare the stability, so I can say that benzoyetine C double bond OH is more stable as compared to phenoxyetine. Benzoyetine is more stable than phenoxyetine. And if you compare the acidity, so final conclusion is benzoic acid is more acidic than phenol, because it is stabilized by equivalent resonating structures, it is stabilized by non-equivalent resonating structures. Even though phenoxyetine will give more number of resonating structures, it is found to be unstable. Okay, so this is stable, that's why it is more acidic in nature. And if you compare the pKa value for this one is, see, this is 4.2 and here phenol is almost all 10. So if you compare the pKa value, as smaller the pKa value, greater the acidity. So pKa value experimentally proved for benzoic acid 4.2 and this is 10. So finally we can say that whenever phenol and benzoic acid having a equivalent and non-equivalent resonating structures, what is the key factor? See this. This is oxygens and here this is a p orbital is present and here one more p orbital and here one more p orbital with negative charge. This is carbanion I am writing. Now here one electron. So these are the pi bonds which are formed here between benzene. Now this is benzoyetine, this one I am writing. Now between carbon oxygen double bond is there. Here one electron, this will be the one. Okay, and here see O minus means this oxygen carry one extra lone pair. So this is extra lone pair, minus nothing but one extra lone pair, minus. Here minus means already two lone pairs are present and here also two lone pairs are present. And here two more, one lone pair and this is one more lone pair. Okay, so this is called benzoyetine. You can also write like this. Benzoyetine structure I am writing like this. Here double bond and here carbon, oxygen and here two lone pairs are present and there is a double bond. And here lone pair. So three lone pairs nothing but O minus. So now see, these p orbitals are orienting in a x-axis. It is completely x-axis. And here this carbon unhybrid orbital, this one, px orbital is orienting in x-axis, px orbital. And here also this is also in px orbital. This lone pair is also in x orbital. So if this orbital is in x, then what happens? See, this negative charge will migrate here and this will be broken up and this electron will be added here. So if you add here, you make it one more resonating structure, that is this one. So this carbon carry carbon oxygen double bond and here p orbitals are as usual. This is p orbital and here one more p orbital. Now see, when this carbon start overlapping with this one, see this. This electron is added here, this electron forms a bond here. Now you make it one more bond. This is a bond and here this oxygen carry that negative charge. Here one lone pair and here one more lone pair. Okay, so 6 delocalized electrons in benzene like this, 1, 2, 3 and here also 2 electrons. Now this negative charges keep delocalizing now. C double bond O minus. Now this negative charge comes from here to here and this bond is going to be broken. Next this bond is going to be broken, come to downward direction. So means back to back identical resonating structures are going to be participated. Okay, so whenever its delocalization is taking place in benzoic acid, see this. This is C double bond O minus, double bond. This negative charge migrate here, it will be transferred up. Now during this case, I can write a pure resonating structure like this. So double bond, C double bond and here it is O minus. Like this. This is a resonating structure of benzoic acid, this form. And this one, see, it is one of this form. Now, these two are interconvertible with a small energy gap. E gap is very less. E gap is very less, means small energy difference. That's why easily interconvertible. Interconvertible nothing but we can write resonance of these two molecules with less amount of energy. And if you want to write hybrid structure, what is the hybrid structure of this one? See, this is oxygen. Here electrons are delocalizing from oxygen to oxygen, and here delta minus, otherwise minus 1 by 2. One negative charge is shared by two oxygens. So when one negative shared by two oxygens, we can write minus 1 by 2, and here also minus 1 by 2. So I can say that this O minus shared by this oxygen as well as this oxygen distributed by minus 1 by 2. So finally, this benzene conjugation never affect this conjugation. See, here two types of conjugations are there. One more concept is there, cross conjugation. See, this is double bond, that is pi bond. Now here sigma bond and here non-bonding electron. Here double bond, sigma bond, and here one more non-bonding pi electron is there. This is pi electron, not non-bonding. Now carbonyl C double bond conjugate with non-bonding. Carbonyl C double bond also conjugate with benzene pi electron. So now the additional factor in this case is benzene is also conjugate with C double bond. Okay, so remember, it is also conjugate with C double bond. Not only O minus conjugate to carbonyl, even benzene pi electrons also conjugate with C double bond. Now the major drawback in this case is, just listen. If I take benzoic acid, you need to remember the cross conjugation concept here. Now, when this negative charge is delocalizing, if this negative charge is delocalizing, here this negative charge migrate and this will be transferred out. Okay, so on that time what happens, see, this pi also have a tendency to use its conjugation. So whenever, if this pi involve in conjugation, responsible to involve in delocalization, on that time this kind of resonance is very poor. This resonance is poor. Okay, see, suppose if benzene is not present, suppose if I take a molecule of this one, here C double bond O minus, there is no conjugate side. So on that time what happens, see, here this will delocalize very fastly. So this delocalization is very fast. This is very fast generally. So forget about this part is not present. It is not involving. This side conjugation is not there, I am saying. But here this side conjugation is there. So this side what happens, see, it is little bit slow. Because this pi electron also want to involve in resonance. Okay. Suppose whenever if this pi electron involve in resonance, you may get this kind of structure. See this double bond, this bond will migrate up and you will get carbon-carbon double bond, and here O minus, and here one more O minus, and here see, it is positive charge. Now this positive charge is delocalized within the ring. Now the major problem in this one is, whenever if this pi electron involve in resonance, it will disturb this resonance. This is called primary resonance, stabilizing resonance for benzoic acid. Okay, so when these pi electrons are involved, this resonance is disturbed, that's why it is slow. Whenever if it is slow, some amount of energy is present within the molecule, it becomes energetic, unstable, and this becomes less acidic. So now I can say that due to cross conjugation is observed here. Due to cross conjugation with benzene, stability decreases. Stability is regularly decreases. Because see, whenever if it is delocalizing, it is indirectly disturbing. This is called cross conjugation. So due to this cross conjugation, I can say that such type of effect is observed in formic acid clearly. Clearly you can observe the difference here. So formic acid is more acidic as compared to benzoic acid due to this reason only. Formic acid, see, here there is hydrogen atom is present, only this conjugation is present. This conjugation involved very fastly, it is more acidic, more stable, more acidic. But see, in this case, benzene is present. Benzene is generally showing a cross conjugation with this one. So due to cross conjugation, this delocalization is poor. But yet this delocalization is very fast because hydrogen is not a conjugate partner. So I can say that formic acid is more acidic than benzoic acid. Okay, reason is this one. So whenever if only this part is involved in resonance, benzoic acid is more acidic. But what happens, additionally this double bond is also contributing, which will disturb the existing resonance. So that's why it is slow. This is fast. Suppose if I take hydrogen over here, if I take only hydrogen, better example this one. If I take hydrogen, this resonance is not disturbed by hydrogen. So on the time, this is found to be stable. Corresponding molecule with proton is more acidic. Now this is found to be less stable, less acidic. So finally, only one conclusion. Benzene and carboxyl want to involve in resonance back to back. That's why this resonance is partially disturbed by this one. And one more important factor, this benzene is also acts as a minus IE group. Suppose if you compare formic acid acidity, formic acid is more acidic than benzoic acid. Benzoic acid is more acidic than acetic acid. This is acetic acid. So I can say this 3 acidity order follow like this, because phenyl is showing a minus I character, methyl is showing a plus IE character. So especially for benzoic acid, after losing proton, the negative ion is get stabilized by resonance. Additionally, it is get disturbed by cross conjugation. Okay, so that is about acidity relation between benzoic acid as well as phenol. So finally, benzoic acid is more acidic than phenol, but benzoic acid is less acidic than formic acid. This, you try to remember this particular format. It is very, very important for variable competitive examinations. Okay, and very, very important one regarding to the resonance stability of benzoic acid. See this. This is benzoic acid, C double bond O, and here it is O minus. Okay, double bond, double bond, double bond. Now these double bonds I am going to write in such a way that it should be planar. Double bond, double bond, double bond. Remember, when benzene and carboxylic acid is present, now after carboxylic acid losing proton, there is a formation of a carboxyl ion. Overall is a benzoate ion. Now the case is, it is perfectly planar. It is perfectly planar. But if you consider carboxyl ion, it is also perfectly planar, because the hybridization of benzene is sp2, and each and every atom in this is also sp2 carbons. So if carbon, oxygen all having sp2 hybridization, both are planar. So the angle separating between benzene and carboxyl ion, it's completely separated by 0 degree. 0 degree means it is looks like a planar, it is also planar. Okay, so here this carbon have a tendency to rotate. So whenever if it is rotated, then what happens? See, here you may expect this kind of molecule. See, this is C double bond O, and this is O minus, here double bond, double bond, double bond. This one possibility is there. Okay, there is a possibility of rotation. See, if these two are completely planar, if benzene and C double bond O minus, C double bond O minus, if these two are planar, like this I am saying, if these two are planar, cross conjugation is possible. So this is possible, this cross conjugation possible. Benzene pi electron involved in cross conjugation. On the time stability decreases. Okay, so I can say this is found to be less stable. Why this is less stable? Because see, here this O minus involving in resonance. Now this resonance disturbed by this one, because this and this both are in planar, in one plane. Okay, so if you compare this one, see what I am writing is, this phenyl is completely in x-axis, otherwise it is a planar. It is planar. Due to some reason, means maybe a ortho substitution is present. I will explain in ortho effect, there you will understand clearly, but right now remember, this carboxylate ion is planar with benzene in this case. Now carboxylate ion is perpendicular to benzene, which means I would like to make a rotation around 90 degree. Okay, so now this is vertical, and what about this one? It is horizontal. It is vertical and horizontal. Now these two are non-planar parts. It is separated by an angle of 90 degree. So try to understand this concept, very, very important one. Steric inhibition of resonance is going to be observed. Our target is to prevent this resonance with this one. So this resonance should be prevented if this resonance is involving, this factor I am saying. So if this and this both are planar, this resonance affected by this one very easily. On the time stability decreases, acidity also decreases. But right now see, if carboxyl ion is completely perpendicular like this, So which means one oxygen is above, other oxygen is backside, and this is completely planar. Like this, CO2 is present like this. But in this case, CO2 minus is present like this. So now this CO2 exactly horizontal, it is also horizontal, but this is horizontal and this is vertical. So on that time, this cross conjugation is not possible. When cross conjugation is not possible, now what happens? See, this carboxyl ion resonance is very fast. So this is very fast and this is found to be slow. Why it is slow? Because it is disturbed by planar benzene. It is not disturbed by non-planar benzene. So I can say this is found to be more stable as compared to this one. And this is found to be unstable because this resonance is not freely taking place within this molecule because here benzene is disturbing. Benzene conjugation is disturbing. So I can say this is less stable and this is stable. This resonance is stable. So if I take a non-planar benzoic acid, okay, generally benzoic acid two forms are not exist, but I am taking a rough example so that you can understand ortho effect. Okay, so non-planar benzoic acid, non-planar benzoic acid is more acidic than planar benzoic acid. Planar benzoic acid. So reason is this one only. Simple. In planar benzoic acid, cross conjugation disturbs the existing conjugation. In non-planar benzoic acid, cross conjugation never exists because it is quite perpendicular to this one. Okay, so this you will see one more time in concept of ortho effect. There you will understand what is ortho effect acidity of benzoic acid. See, I want to bring this carboxyl ion exactly perpendicular to benzene. So for that, I would like to substitute one group over here. If I substitute a group at ortho position, that will prevent planarity of this carboxyl ion with benzene. So on that time it is exactly vertical to benzene. So this and this not involved in resonance. Okay. So that is about phenol versus benzoic acid as well as acidity relation for planar benzoic acid as well as non-planar benzoic acid. Okay. Just make a short revision. See this. Phenol versus benzoic acid. If you see the phenol and benzoic acid, both will give a corresponding conjugate basis, phenoxyetine and benzoyetine. Acidity depends always on stability of conjugate base. It is giving more number of resonating structures, but it is giving only 2. Even though it is giving more, it is less stable and this is more stable because this gap, energy gap to convert one resonating structure to other resonating structure is very less. But here energy gap is very high, means unnecessarily it is wasting the energy. Okay, so means one resonating structure, if you want to convert into other, some amount of energy is required. But here very less amount of energy. If this gap is decreases, energy gap of interconversion of resonating structure decreases, stability increases. So due to this reason, even though phenoxyetine carry more number of resonating structures, it is less stable and this is more stable. Okay, next. See in this case, stability if you concern, benzoyetine is more stable than phenoxyetine, benzoic acid is more acidic than phenol. Finally acidity, pK value is very less for this and this is very high. As pK decreases, acidity increases. Finally see the p orbital overlap as well as primary resonance, secondary resonance, I am explaining clearly. So this CO minus you can write like this. So this lone pair is participating in resonance and this pi bond transfer here. You will get this structure. Okay, so this is contributing now, here lone pair and here 2 electrons are present. 2 electrons nothing but lone pair, this O minus. Okay, so when this negative charge involved in resonance, this pi bond is going to be broken and this electron will be added here. Finally, you will get negative charge. Now, these two you will get. Later on, what happens? See, whenever if this negative charge is delocalizing between these two oxygens, you will get minus of minus 1 by 2, minus 1 by 2. Right? Now, this resonance, if stability increases, acidity increases. But this resonance is disturbed by benzene because benzene also conjugate with carboxyl ion. So due to this reason it becomes very slow. So when benzene pi electrons are conjugate with C double bond O, on that time right side resonances get disturbed. That is called cross conjugation. Okay, so due to benzene cross conjugation, this stability decreases, it is slow and this is fast. If this is fast, it is more stable, it is less stable. That's why formic acid is more acidic as compared to benzoic acid. Okay, so finally one more conclusion based on the orientation of carboxyl ion and benzene. If carboxyl ion and benzene both are planar, less acidic, If carboxyl and benzene both are perpendicular, more acidic because there is no cross conjugation. That is your final conclusion of benzoic acid. Okay, so that is about this concept. Hope you people will understand. It will be most helpful for ortho effect. First you listen this class, then ortho effect will be understood very clearly. Okay, so try to subscribe our channel and you will get such type of new videos regularly in your app as well as YouTube, so that you can get a more clarity on the concept, and it will be a motivating for our institute as well as even we are also providing a regular videos in competitive point of view. Okay, this is a conceptual point of view. Even competitive point of view also we are taking videos, and that videos will be most helpful for IIT advanced level as well as NEET examination. Okay, so thank you for watching this video.